Good morning, afternoon, and evening, depending on where you are watching. Thank you for joining this session. While there are many sessions in parallel, my name is Kazuaki Ishizaki. Today, I'd like to talk about brief overview of Apache Spark 0.0 improves performance your SQL application. I put this presentation into my SlideShare after this talk. So let me introduce myself. I'm a researcher at IBM Research Tokyo. My expertise is compiler optimization. I became a committer of Apache Spark 2 years ago. I have been working for SQL package, in particular, whole stage coordination and interaction with Java Virtual Machine. I have been working for IBM Java Virtual Machine over 20 years, 1996. In particular, I was responsible for research and development for Java just-in-time compiler. So Spark 3.0. What we are waiting for a long time since Spark 2.4 has been released. Here are major changes in Spark 3.0 for SQL performance improvement, which I personally selected. Spark 3.0 improves interaction with developers, introduce new dynamic optimization without manual parameter tuning, apply optimization more cases, and update infrastructure Java and Scala. Let's see recent history of Apache Spark release. Let us go back late 2018. The community released Spark 2.4 on November 2018. At the last Spark Summit at San Francisco, at the keynote, here is an announcement, Spark 3.0 expected later this year. It means 2019. Unfortunately, it did not really happen. Instead of that, late 2019, the community released the preview release of Spark 3.0. It was 1 year later after Spark 2.4 was released. So congratulations, Spark 3.0 has been released early this June. So community extensively worked for releasing Spark 3.0. There are about 3,500 issues that community reported fixed, including new feature, improvement, and bug fixes. 3,500. It is hard to understand what's new for SQL performance improvement. So in this Spark Summit, there are multiple sessions to explain, introduce, and deep dive new features for Spark 3.0. So this session guides you to understand what's new, focusing on SQL performance. Here are a list of 7 major changes from my perspective. So please vote which item you are interested in, among them within next 1 minute. So obviously, there are other many changes. If you are interested in other changes, so please join other sessions to follow them. So these 7 changes can be categorized into 4 areas that I already talked in this session. The first 2, new explain format and all type of join hints. They are related to interaction with developers for performance understanding and improvement. Items 3 and 4 are dynamic optimization without manual parameter tuning. Item 5 and 6 are catalyst improvement to apply optimization to broader range of catalyst SQL programs. The last item is update of the Scala and Java version. This is because Spark 2.4 supports their old version. So first, let me talk about new explain format. So what is important to improve your SQL application performance? It is definitely important to understand how your query is optimized. So to understand query plan, it is necessary to easily read it. So obviously. So here is a simple query. Let us see how this query plan is shown on Spark 2.4 and 3.0. On Spark 2.4, when explain command is executed, the displayed query plan is too long. One line is too busy. This is because one line has many attributes. Unfortunately, it is not easy to understand at a glance. So Spark 3.0 introduced new option, formatted, to show a query in two parts. The first is a set of the operator. The second part is a set of attributes. In the first part, in bold, it makes us easy to understand at a glance what operation will be executed. If you want to see the detailed information such as the input and output column for each operation, you can see attribute part for each operation in the second part. For example, you can connect between first part and second part using the number. For example, number 1, number 2. So let us go to second change. This is an extension of join hint. On Spark 2.4, we can set only broadcast join as a hint if Catalyst selects other join type that we do not expect. From Spark 3.0, we can set any of all of join type as a hint if Catalyst selects other join type that we do not expect. Here are examples how to specify join hint in your program in CKL or data frame. So it is important to easily understand query plan to know what join type is selected by Catalyst. If the selection is not suitable, you can suggest better join type by using this feature. Let's go to next category. Adaptive query optimization. This can automatically tune 3 types of parameters by using runtime statics information. One is number of reducers. Next is join strategy. The last is number of the partition for skewed join. They are done automatically without tuning property run by hand. According to Databricks blog, this query optimization can achieve good performance improvement for DPC-DS query. This is an automatic selection of number of reducers. This is a first item. Spark 2.4 determines the number of the reducers using the property Spark SQL shuffle partitions. If one task has 5 kinds of keys to be grouped, the 5 reducers will be launched for 5 partitions, regardless partition size. Therefore, assigned partition may cause unbalanced workload at each reducer. For example, reducer 0 will finish very quickly. This is because partition 0 is very small. On the other hand, reducer 3 takes much time. The total execution time is dominated by reducer 3. Obviously, this is inefficient. This is because reducer 0, reducer 4, they have lots of the idle time, while other reducer is busy. So Spark 3.0 selects number of the reducers to meet the average partition size. In this case, Spark 3.0 will launch 3 reducers. One reducer will have 3 partitions. Now all reducers take similar time. This is efficient compared to in previous page. This is because same things will be done. 3 reducers versus 5 reducers. To enable this feature, we need to set these two properties in the bottom of this slide. The next one is to select join strategy. Spark 2.4 decides join strategy based on statically available information such as table size, 100 GB or 80 GB. At the query optimization time, the size of filter result table 2 is unknown. Therefore, sort merge join is selected in this case. Spark 3.0 automatically changes join strategy based on the runtime information such as size of the filtered result. In this example, Spark 3.0 dynamically apply the optimization based on the runtime information size of filtered result. In this case, the filtered result is very small. Spark changes the join strategy from sort merge join to the broadcast join. As a result, total execution time will be reduced. This is because two sort operations are eliminated. To enable this feature, we need to set the property at the bottom. The last one is to optimize skewed join. On Spark 2.4, partitions are naively created at the join time. Therefore, sometimes skew occurs like partition 2. This is because total time is dominated by processing partition 2. That is the largest partition in this join. On Spark 3.0, larger partition is split into multiple partitions to make their size smaller. Now partition 3 does not dominate the total time extremely. As a result, total time will be reduced. Therefore, the dark purple is shortened compared to the previous page. So Spark automatically duplicate partitions correspond to the split partitions. Without manual tuning run by run, this decision, splitting, and duplication are performed when we set these two properties at the bottom. So let's go to another dynamic feature. So dynamic partitioning pruning can reduce I/O accesses by avoiding to read unnecessary partition using predicated pushdown. This pruning is automatically applied. According to presentation in the last Spark AI Summit in Europe, this can achieve the great performance improvement in TPC DS query. This is an overview of the naive broadcast hash join on Spark 2.4. In this case, all of the data, both tables are read. The result of filter's table small is broadcasted. Then a broadcast join occurs. Since the table large is very huge in the left-hand side, lots of the I/O occurs and wastes the lots of the time due to the reading unused data at the join time. Dynamic partitioning filter allow table large to perform the predicated push down to avoid reading the unnecessary data. The dynamic filter information is sent to the broadcast data. The dynamic filter information based on the filter operation in the right-hand side. Then, when table large is read, pushdown is applied based on the dynamic filter information. Finally, only the necessary partition is read from table large. It can drastically reduce amount of the unnecessary data to be read. Then we can improve the performance in this query. This is an example of dynamic partitioning pruning. As you can see in the physical plan, the table large uses dynamic pruning information in partition filter written in blue. This information used for pushdown in packet storage. As a result, a table large can reduce the amount of data to be read. Let us go to other category, catalyst improvement regarding the nested columns. The first improvement regarding the nested column is a column pruning. Column pruning can read only necessary columns from packet columnar. On Spark 2.4, column pruning works for some operation such as limit. As you can see here, only the nested first column in column 2 written in blue is read. We can successfully avoid reading unnecessary data like a column 1, second column in column 2. On implementation of column pruning for nested column, it was ad hoc in Spark 2.4. For example, it does not work for other operators such as repartitioning. As you can see in the bottom, both columns are read and repartitioned. After repartition, pruning is performed. When we compare both cases, the bottom one is inefficient. This is because bottom one are read 2 columns compared to the upper one. So upper one read only 1 column. So Spark 3.0 fixes this issue. Spark 3.0 can apply column pruning to nested column with any operation. It can improve the performance for any operation for column pruning. Here are example programs for column pruning. As you can see, both query, limit, and repartitioning read schema in packet have only column to the first column. Therefore, packet will read only 1 column. We can reduce amount of the I/O by avoiding read unnecessary data. Another improvement regarding the nested column is a pushdown such as packet and ORC. On Spark 2.4, pushdown works well for non-nested columns such as column 1, written in orange. However, it does not work for nested columns such as column 2. As you can see query plan, pushdown filter does not have a condition regarding the term to 1 equal 100. As a result, all partitions are read from packet columnar in Spark 2.4. Spark 3.0 fixes this issue. Pushdown in packet and ORC works well for nested column. As you can see in blue, so blue expression passed to the packet, then packet can apply predicate pushdown. So packet does not send all of the data to Spark, but send only the necessary data partition, only a part of column. Therefore, we can improve the performance compared to the without pushdown in previous page. So generally, the nested column is used in complex and large schema. It will be useful handling complex and large data in your use case. You can improve the performance such a case. So next one is an improvement for complex aggregation. On Spark 2.4, a complex aggregation query is slow. This is because the query is not translated into the native code. For example, it happens in TPC-DS query. Why it happens? Here is a quick overview of how query is translated into native code. A given query is translated to Java code by Spark with a query optimization in Catalyst. Then Hotspot compiler in OpenJDK translates Java code into native code. However, if the Java code is too large, Hotspot compiler gives up generating native code. Thus, the performance is not good. So Spark 3.0 fixes this issue by making aggregation Java code small. Spark 3.0 splits a large Java method into small methods. Then Hotspot compiler can generate native code for multiple small methods. As a result, performance is improved compared to Spark 2.4. So here is an example program to perform average function to 50 columns. Now, generated code size is small, as you can see in blue. All those methods up to 8,000 Java byte code per method. All of the methods will be translated into native method by using the Hotspot compiler. When we disable this feature, the size is more than 8,000. You can see in red part. The native code will not be generated by Hotspot compiler. Therefore, the performance is not good compared to the above case. Finally, let me talk about updating Scala and Java. On Spark 2.4, Java 8 and Scala 2.11 were officially supported. From Spark 3.0, Java 11 and Scala 2.12 are officially supported. Java 11 has multiple improvements for native code generation and garbage collection. Therefore, in general, the performance will be improved. And from the maintenance view, OpenJDK 11 is a long-term support version. It will be supported by 2026. In the Scala side, Scala 2.12 exploits new feature of Java 8. This is a good compared to the Scala 2.11. So here is a takeaway. Spark 3.0 introduces many features for 1.5 years. From my perspective, these 7 features help performance improvement for your SQL application. If you want to revisit this presentation, please visit this SlideShare URL tomorrow. I will post my presentation after this talk. So there I put some resource good to read at the blog entry and presentation. Thank you for your attention.